So I am Joe Rickert. I'm a program manager at Microsoft and an R evangelist. I represent Microsoft on the R Consortium, which is a business alliance of interested companies working in the R ecosystem to work on projects that will improve the infrastructure for R. So there's a big announcement about this yesterday, and we can talk a little bit more about that later. But so the first thing I want to say is this is a hands-on session, but it is not a race. Okay, I will be moving quickly through material, but I believe that the way people learn is to see things multiple times, touching things. So what I intend to do today is help you learn how to learn about R. And all of the material that we'll be on the we'll be using today, which is on the folder under the Data Insights folder under R Studio, is also available on my GitHub repository. So don't worry about it. You don't get it today, you can take it home and you can work with it. So what I hope to get across here is that R is approachable and it's fun. Yesterday, you probably saw many sessions where people were talking about how R was being embedded in SQL Server or working with PowerBI. There's ways to work with Excel and R. And you're going to see more of that. What's happening is that open source initiatives like R and Python and some others, Hadoop to some extent, are now providing the undercurrent that's driving innovation because of the thriving communities. And Microsoft is embedding these as kind of glue, the analytics glue that is binding all these products together. So my impression is that people who have some knowledge of R are going to find this to be a very lucrative path to follow, because all of you have business experience. You know the domains that your clients are working in. You'll be the ones who will be able to leverage the open source products, open source R, inside of the Microsoft products. So that's where we're going today. And as I said, I hope to make it interesting and to let you know that you can approach this at a pace that suits you. So what is R? So three things. First off, it's the most powerful statistical programming language. It's actually built to do statistics, and it has structural features that facilitate this. It's a functional language. It means you work with lots of functions, and when you write a function, you put the same inputs, you always get the same output. So it's not like it doesn't change the state of your machine. And it also has an object structure, and the objects happen to be particularly convenient for addressing statistical ideas, and we'll see what that means in practice. It's also a great platform for visualizations. So the visualizations took on a life of their own, and we'll see some examples of this. But first off, I want to make clear that there are levels of visualizations. So first off, if you're a working statistician or data analyst, you might want to get a really quick plot that has some illuminating feature of the data, unadorned very quickly. And that's how the visualization in R started. It wasn't for visuals to show somebody else. It was visuals for people to consume, the statistician to consume. Since, it turned out that R was so good at doing that, that you'll see that there are quite a number now of ways of writing, of building very compelling graphics in R. And then it's also the case that with R being embedded in different products that you might want to use for your final presentation, something like Power BI. That's fine, you know. So the point is there's different levels of getting access to pictures of the data. Most importantly, R is an open source community. So it's a thriving community. What that means is that once you start to get involved, either you know, just by teaching yourself, you get online, you search for things, you come across other people who are doing the same kind of thing, you realize that you can become formally involved. There are open source, there are R user groups throughout the world, there are conventions, there are conferences, there are many informal ways where people meet both online and in person. So a little bit of history. So it's interesting to know how things got started. R started in 1976 at Bell Labs. And the statisticians there, John Chambers, Trevor Hasty, and a number of others, they were interested in providing an interface for their really rock-solid Fortran programs that were really hard to get to. So that's what they didn't intend to develop a programming language. They intended to provide statisticians with an interactive platform so that they could do data analysis conveniently. Now, as it turned out, over the years, R developed into a very powerful programming language. But the initial idea still holds. You know, nobody who's a developer in R thinks that R is going to be the be-all and end-all. But what people hope is if there's something cool out there, R will be able to connect to it. And that's what you're seeing even here inside of Microsoft. Whatever the next big thing is, there's going to be somebody in R working to make that happen. So the rest of the thing, what happened is that when AT&T divested, the original language was called S at Bell Labs. AT&T actually shipped it with Unix for a while. Then AT&T divested the Bell Labs. S became a proprietary software. That ticked off a lot of people in the open source community. So two guys actually re-implemented the language. Those two gentlemen there, Ihaka and gentlemen, they re-implemented it as an open source project. And you can see it was incubating from the early 90s to where we are now. So the R ecosystem. So I mentioned the community. The way the R project is run, you can go to rproject.org and you'll get to the main page of the group that runs R. So there are about 20 core developers. So the language is very small. There are only about 20 people who make commits. The language itself changes very slowly. The language is managed by the R Foundation, which is a European-based organization that holds the copyrights to the open source R licenses. And as I just mentioned, there's now something called the R Consortium, which is a group of several companies, and I'll show you the website in a minute, that are working, right there. Is this the sweet spot? Is that better? All right, so the R Consortium is working on projects to facilitate the infrastructure that supports R. After all, for all these 20 years, the R language has been basically developed by volunteers. And now that companies such as Microsoft are depending on R to be there as part of its, its long-range business, the community, the companies are contributing to the community by undertaking projects that will benefit everybody. One of the most important things to know about R is that it grows through packages. So packages are libraries of functions. Anybody can write a package. There are now over 8,000 packages on the CRAN repository. So 8,000 packages. What happens when a package goes there is that if it's good, it immediately gets the attention of experts throughout the world. So since anybody can inspect this, the source code, when people start to use it, they inspect it. So it's like a totally crowdsourced by experts quality control. Not all of the packages on CRAN have that same level of quality. And that's probably one of the most difficult things that you'll face is finding out what you need. How do you sort through the 8,000 packages? And I'll give you some ideas on how to do that. What I'm showing there is a social network analysis, a portion of a social network analysis of the R package system. So treating packages like they're people, and the lines indicate that one package is called by another package, depends on another. So you can see that there are a great complexity in the interrelations, and that there's grows in an organic kind of way. Here's this is a little bit outdated already, but here's the kind of exponential growth that's happening. So our package is collections of functions. On the average, say, there's about 10 or interesting new functions in each package. So what happens is that there are like hundreds of thousands of available functions for you to use in R in your work. These are the packages that form the core of the language. So when you come across one of them, you'll know that they're automatically loaded for you when the system is brought up. And the major way that people look for packages that pertain to their area is through looking at what are called task views. So if you just search for task views on your favorite R task views on your favorite browser, you will see that there's a page, and these are that list them, and these are curated collections of packages. So these are the ones that experts have looked through and identified as being fundamental to their particular area. Now that's so that's the first way to look at packages. The basic takeaway point is that you all have some particular interest that the reason why you're approaching R. And R has probably got some analytic software, no matter how obscure your interest may be, has some analytic software that pertains to that. So finding that might take a little bit work. But once you find it, you'll find yourself in an environment where there's a lot of help for you, and it'll be easier to go further and learn more, and you can become an expert in your area. There are lots of online help and books written about R. So if you're interested in R for finance, you'll find books that are just R for finance. They'll cover the basics, and working through one of them will be like the next step for you to progress. Forecasting, there's an online book for forecasting that's free, that's excellent, written by one of the prominent experts in time series forecasting. So if you're a biologist, the same thing. I imagine most of you have a business interest here. So you will be able to find books that use R code for modeling and marketing kinds of situations. So the thing to do is to orientate yourself, then become involved in that sub-community, and just ask around, ask for help. Here's one place you can go. This is the MRAN site. This is managed by Microsoft. It was originally set up by Revolution Analytics, the firm that Microsoft acquired, from which I came from. And you can find, what is R. We'll go into even more detail than what I've been just telling you here. You can download the same Microsoft R Open, which is the open source distribution of the R language that we're using today that has been enhanced by Microsoft. And you can find information on packages. You can search through packages there. So let me say something briefly about distributions of R. So the fundamental thing is that Microsoft R Open is a distribution of the R language. It is not a fork of the language. So it's the same open source R that you can download from CRAN. What's different is that we've added some linear algebra libraries that get compiled in that make the code faster for linear algebra type functions. So these are kind of, anybody can do this kind of thing. It doesn't cost much to license these libraries from Intel, but Microsoft does that and just makes it available to everybody. So it's a little more high performance distribution of the language, and there's also a couple of other packages that are folded into that. On top of that, Microsoft has Microsoft R Server, which is the, it starts with Microsoft R Open underneath, and it adds in a special package of functions that are meant to work in distributed computing and automatically, they automatically produce parallel functions. So there's two levels of working with R in Microsoft. There's the same open source R language that we're focusing on here today, and then there's the level of Microsoft R Server, which contains proprietary components. So learning R. So this is how I see things, and it's been the way based on observations of participating in lots of user group meetings and talking to customers. This is the way things work. So on the bottom, you got your Malcolm Gladwell scale. And basically, he says that if you want to do anything and become an expert, it's going to take you 10,000 hours. Whether you want to be a rock and roll player, or a bridge player, or do R, you got to put in 10,000 hours. The Y scale, though, reflects different levels of skill that you might acquire if you stick with R. And what you see here in the middle with the yellow are levels of competency. So my contention is that most people work in this area here. So it's a very approachable goal to be able to be competent in some area and make contributions in R without having to be a real expert. And I hope to show you today as we go through things that that you can do stuff right from the beginning that will be helpful. So the way we're going to do this is I'm going to talk for about an hour showing you code, which you're welcome to kind of work through. There are 3 levels of files you have access to. Things that end in .r are scripts that you can execute and follow along right with me. The things that end in HTML are HTML files, and they're like polished versions with a lot more text in there that describes what happened in the .r scripts. And there are also the markdown files that I've included in there. So on your own, when you take these materials later, you can change the R markdown files and use the RStudio editor to make your own HTML files. So it's a way for you to generate a little bit of your own material. And I'm going to, as I said, I'm going to go through some things together, executing from the scripts, and then I'll probably switch to using the HTML just so I won't have to type and I can talk a little more. And then for the last 20 minutes or so, there are some extra modules that I won't be able to cover in detail, but that you can investigate on your own, and our proctors can help you if you need it. So let's get going. So how do I switch between monitors? Great, already done. So here what you're seeing is this our consortium page, and you can see the companies that are members of the R consortium. So you might want to look at that, investigate. Here's the MRAM page. You want to find the package. You type ggplot2, and it should search for that package. And here you see stuff that are, because ggplot2 is so popular, you can see here it is, and you click on that, and then you can see that this particular package has a PDF, so every R package, that's the way the documentation works. This is just the, the technical explanation of what the functions do. But you really want to look to see whether a package has a vignette. A vignette is something that's more user-friendly with examples, and most of the really good packages have vignettes. So that's the way to get some online documentation. Here's the R project. The official site is at CRAN. So you go here, and there you can see who the contributors are and information that I was talking about before. And here's what the task views look like. So when you go to search for task views on the R project, so you see here's one for machine learning. And here you have the way things look. There's usually a short description of the packages. The ones that are most important are in the main paragraphs. And you can see that Torsten, who maintains this task view, has divided them up to different kinds of machine learning techniques. So you'll find looking through task views very helpful. And here's the GitHub link that you had before. So to get all of these materials that we'll be using today, you can just go home and download them on your own. Here, again, R files are the scripts we're executing. These are our markdown files, versions of the scripts that have the markdown language, meta language in there that produces these HTML files. So let's open up. You open up your R Studio IDE, it should look something like this. We'll be working primarily in this window here, which holds the scripts. So you can see where I am, upper area here. And this is the interactive window. So the first thing I'm going to do is Control L will clear that window. And let's just, I'll do a little free form, then I'll go through the script. So first off, R is an interpreted language, so 2 + 2 = 4. So this is what the output looks like. You have the little caret, which is your prompt, and then it produces the sum, and it shows you that there's one result. That's what that one in there looks like. X gets... So let's just do 100. So first off, I'm assigning this the equal sign and with the hyphen next to it. This is the assignment operator in R. So I'm assigning some value to the variable x. And what I'm doing here is actually a simulation. So this is one of the reasons why R is so powerful for doing statistical work. So what this little function does is say, draw 100 numbers from a random normal distribution that has mean 0 and variance 1. That's the default.
Joe, there's a question from the audience. Can you zoom in a little bit for us?
Can I zoom in? I don't know. Let's try.
The Windows plus key will actually zoom in, and Windows escape will zoom out.
Yeah, but it's not,
Okay,
it's not happening for me.
okay.
Let's try again. Oh, maybe that's too much.
Just Windows Escape will get you back out. And it'll go to wherever your cursor is.
Yes, so is that all right? All right, so what I want to, so where we are is it drew some numbers. Now the first thing you notice is that nothing happened, and this is typical of R. You don't get output until you ask for it. If you type in X now, I'll get all of the random numbers. So typing it in will produce it. The name of the variable will show you what they are. One of the first things you might want to do is get help in R with a function. So our norm was a function. This guy was a function. If you type question mark our norm, you'll see over here the help for that function will show up in the window. If you type our norm by itself, you'll get either the source code for the function if it's something that that you've written, or you'll get some gobbledygook for functions that are core to the R team and are really written underneath in C and what have you. But so you can use this to interrogate functions most of the time. So now a couple other things. Let's go through the script. So the way to do this is first just look at the script in the window here. And you can see that I've got stuff in green and other text in black. So the green are comments. And the way you indicate a comment in R is the hash sign here. And if we can execute some comments, they'll just reproduce down here. But you see what we've done here is, again, just a couple little yeah, I couldn't get that to work before. It's not working. You try it.
Where's plus? Okay.
Is that better?
Yep.
All right, thank you. All right, so what we've shown here is the 2 plus 2 again, and then different functions. So R has many built-in functions. Notice that I was able to run 2 functions on the same line by separating them with a semicolon. Now, lots of times you're going to have a big arrays of numbers, so what you want to do is to be able to see portions of your data. So, by the way, you can either execute a line of code by highlighting it and hitting run over here, or you can do Control-Enter, and that will show you. So here I looked at the head of that 100 numbers, so I got the first 6 by convention. Then I'm going to do the tail, the last 6. Here's a convenience function that you use a lot called length. It'll give you the length of, not control. So it was 100 numbers. I can get a summary. So I do summary, and I get a standard kind of 6-point summary that you'd want to make it, to take advantage of an array of numbers. You get the mean, the median, the min, the max. I can just go ahead and plot those numbers, and this is what I mean by this is kind of a raw, unadorned plot that you can get in R. You can zoom onto this plot if you want from here and save it if you'd like. Not pretty, but it gives you, you can see that these are random. So, and you can do a histogram, again, a normal kind of unadorned histogram. with a little bit of work, you can get prettier histograms. So what we're doing here is we're generating the histogram and using and I have frequency equals false because I want to actually make this a density so I can put a density curve on top of it. So this is typical of baseline graphics in R. This is a typical baseline graphics plot where you have some parameters in the histogram itself. I'm using them to make it pink. I have a curve function which will lay a curve on top of another plot, and then rug which will lay on the bottom. So the rug shows you exactly where the data points are. So this is a good way to look at a distribution in general. So you've got a histogram with just the default settings. Of course, when you want to study the data, you want to change bins and everything, and there are ways to do that in R, and you can look at that later. And also a density, and you'll look at density estimates. Here's an interesting, well, first off, I want to say before I leave plots altogether, there are 3 basic plotting systems in R. And we will have a look at all of them today. And basically, you don't have to work in all 3 of these systems. In fact, most people who are experts just work in 2 out of the 3. So you pick the baseline, and then you have one or the other. And I'll show you what they are later. I want you to be able to recognize where they come from, where plots come from. And we'll see that as the day goes on here. So now what I'm doing is assigning a vector of numbers from 1 to 10. So here's another way to assign to y. So I do that. And now if I type y, you can see I've got, oh, I didn't mean to do that. Control Enter. Oh, it tried to do y. So there's a kind of mistake. I made a mistake. So I went to hit Control Enter, and what I did was I hit Shift Enter, and I put a y, so that now they think there's a variable called yy, and it's not found. There's no variable. It's not found. There is no variable yy. So the point here is you're going to make mistakes, and don't sweat it. I mean, you can't break anything. You know, just re-edit. I'll re-edit my script and try it again. When you make mistakes, so here's the first 10 numbers. And now, this is a very important point here. R is a vectorized language. That means you're usually working with arrays of numbers instead of individual numbers at a time. And the consequence of that is that there's very little need, especially when you're first, starting to do things, to write for loops. Usually there's a way, a vectorized solution to something. So for example here, we're going to execute these 2 lines of code, which will, the first one adds 2 to every number in y, and the second multiplies every number in y by 2. So there is, that's a first little idea of vectorization. And we'll cycle back and see a little bit more of that later. Another good thing to know is that playing with these functions, and you want to have some data. So you can generate data the way I did just then, but R comes prepackaged with a lot of data sets. So when you do, see that data with, I'm executing the data function, and it's showing me different data sets that I have access to that are just loaded in the packages that I have available to me. So you can see here, if I go to packages, this is all that I have installed, and so I haven't done anything yet, installed any, pardon me, they're installed but not loaded, and I'll show you the difference in a minute. But these are data sets that are just always there for you to play with. And let me close that. And what we'll do is now I'm going to load a particular data set, the empty cars data set. And up here, you may have noticed that things are popping up now. And this is my environment. This is showing me variables that are in the environment with a little bit of summary. So it says here that I have a vector x, and it's got 100 items in it. I've got y that is integer. This is numerical. Empty cars is a promise. Well, R is kind of lazy. R does not actually put stuff in the memory until you execute it. And now that I'm going to ask for help, that should change. So now you can ask for help about data sets. Help is the long way of doing the question mark. So you can either do question mark empty cars, or you can do help empty cars. And you see over here in the window of the RStudio editor that there's the documentation on what the variables in the file mean. Let's go through and we'll look at the head. So that's a good thing to do. So now you see that we've got these columns, and they're miles per gallon and cylinders and displacement and what have you. And over here we have row names. These are row names. These are not variables. These are a way of identifying the names of the rows, and we'll look at that a little bit later. But what you see is the primary data structure in R. It's a data frame. And in the next module, I'll go through and show you some different data structures. But what's notable about this, first off, it's the way that statisticians think about things. Each row is an observation, and each column is a variable if you're a statistician, or a feature if you're a machine learning kind of person. So it's rows and columns. It looks like a matrix, but it's not a matrix, because in a matrix of numbers, like how many of you work with matrices in math? Everybody remember their math? All right, so some people do, other people maybe not. But in matrices, every item has to be of the same type. But in data frames, you can have some columns that are integers and some columns that are factors, and we'll talk about what that means a little later, and some that are character vectors. So they're all together. They're like independent features. And this is the structure that that you work with mostly in R. And as you probably already thought, hey, that looks like the way I do things lots of times in Excel. So you could see yourself building an Excel file that has the data the same way. And indeed, one of the primary ways to get data in and out of R is to go between .csv files and data frames like this. So there we have it, first little structure. And now here's a new function that tells class. Class tells you what kind of beast this thing is. So it says it's of class data frame. So as you go through, you'll want to make sure every now and then that you're working with the class of object that you think you have. So you might not know it's a data frame. And one of the things that I should have done here, I think, is type dim. Empty cars. So it tells me it's a 32 by 11 array. 1, 2, 3, 4, 5, 6, 7, 8. Where are we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are the variables. These are kind of attributes to the data frame that name the rows. You don't usually have these kinds of row names. It's a kind of extra feature, but I want you to see that it's there. Now, here's the thing. So suppose I do dimension x. It's telling me null because x is just a vector. So in a vector, you don't do dimension x. What happens if I do length empty cars? Then I just get 11. It gives me just the second dimension. So that's a little quirk. So remind yourself, if you're going along and you did length and when you should have done dimension, or dimension when you should have done length, it's no big deal, but that's the way things work. Here's a function. So when I'm working with data in a data frame, these individual guys can be got at, but it takes some indexing into the data frame, or which we'll do in a little while, or there's this function called width. So I'm going to use this data frame, and I'm going to compute the correlation of two numbers. So it's telling me with empty cars, correlate the drat data, the drat variable, which is here. I forget what that is, but that was listed. Where is drat? Drat is the real actual ratio, and miles per gallon. So yeah, is there any kind of correlation there? And wow, yeah, it looks like it's pretty much correlated. It's better than there's some correlation. And now I can plot. I can plot this. So it's done a scatter plot. And I can do correlation on the entire data frame. And I got the correlation matrix for the whole data frame. Now this leads to an interesting idea in R that makes R a little useful. It's the idea of polymorphism, that the same numbers, the same functions rather, can be used on different kinds of objects. So if I do, we already saw summary X. I can do summary empty cars. So the point here is that the same summary function knew what to do with different kinds of animals. And that's this idea of polymorphism, or, you know, it's a generic function. So what happens is when people, in baseline R itself, you know, the core of the language, there are some of these convenient helper kinds of ideas that are used all the time. You want summaries of various kinds of objects. So what they did was they wrote particular methods for a method for vectors, a method for data frames that has to do with you know, what you want to see for a particular kind of object. And likewise, you can do plot. I can just do plot X. So it plotted one variable against an index because that seems to be, you know, that's a, and I can do plot XY, and now it'll produce, let's see, yeah, so what Y is, let's redefine Y. And now do plot X comma Y. So the same plot function knew what to do with two numbers. And now what's happened, let's plot empty cars. Wow. So what it's producing, it's too small to really see. Let's zoom in a little here. But that's really cool. So there's a method that lets you see pairwise correlations. It's just built in. Basic unadorned plot, but now you can see how these variables relate to each other. And this is the idea that I had with our graphics, starting from visualizations that are interesting to statisticians. You want like a 1 or 2 click thing to get you a picture of what's happening. So it's not the thing you're going to show your boss. We'll show you some of that later, but it's the kind of, or your customer, but it's the kind of thing you want to have available. Now we're going to go to a little more, let's look at this concept of apply. So there's a whole family of functions, apply family, that helps you do things in parallel. So this sapply is kind of it's a nice version of the list function for working with lists, and data frames are kinds of lists, and I'll talk about that in a minute. But it's going to use this scale function on the empty cars data set and put it into a data frame. And you'll see in a minute why I want to do that, because I want to produce a box plot. So if you're comparing a block, if you're doing a box plot which shows the distributions of functions, you want to have them all centered and scaled for comparison. So here's the variables that are in the data set, and you see that the black line represents the median value. A couple cases there are outliers, a little bit of dots up on the upper right. You can see how these variables, some of the variables are, the distributions are wider than others. And it's just a good way to learn your data set. So you do some exploratory work right there. And now we're going to fit a regression model. This is the syntax that R uses here. So you see linear model is the function LM, builds a regression. And what I'm doing is indexing into my data frame here by talking about, so I have empty cars, and the $ says get the variable miles per gallon, and regress that against the variable called drat, and we'll put that in a model. And now I have a regression model, and typical to R, it didn't do it. You don't get lots of output out. You got to ask for it. So first, we'll just ask for summary, and here you see that it gives us a summary of. This is a statistical summary of the model itself, and again, it's the same summary function. It knew what to do with the model, and you can have here the coefficients, the intercept, and the drat coefficient, and it gives you the R squared, so it's not a particularly good fit. You see it's got a low R squared, but this is a statistical summary. In R, one of the features, or some people think, hassles of R, is that there's always more than one way to do something, and I just think that makes life interesting. Here what we just did is run the ANOVA function to get a summary. And now I'm going to do another plot. So I'm plotting and now I'm going to add the regression line on top of it. So there you go, you add the plot. And before we leave this idea, I want to show you a couple more. So let me clear this. I'm just clearing the console here. So we have class X was a numeric. So X is kind of a basic atomic function, and its class reverts to being numeric. We saw that the class of empty cars was a data frame. The class of Reg 1, cannot type, is LM. So it's an object of class LM. So this is the way you get to know what kind of animals you got running around in your R zoo. And now what I want to do is look at the class of all of the objects that were in MT cars, all the variables in there, rather. So I'll do my sapply again. Sapply, and to MT cars, and class. So now what it did in parallel, it computed the class of all of the different variables in MT cars. So you see that they're basically all numeric variables. So it's what you'd expect, nothing different in there. Structure is a command that produces a lot of output. You might not use it too much at first, but you should know that it's there. And what it does is tell you everything that's going on in your object. So I gave it a pretty complicated object. A model, a linear model, is an object that contains all of the kinds of stuff that's interesting to a statistician. So it's got the coefficients in there, and the residuals in there, the rank of the matrix, the fitted values are in there. All this kind of stuff that in other statistical packages are printed out whether or not you want to see it or not is all packed in here, along with some obscure stuff. Well, here's this is about here's the residual degrees of freedoms, and here's the call that was made to actually execute that. And then there are attributes, and there are lots of things. We won't go into all of this, but what it means is that you have available everything that's interesting to a particular class of model you might want to run, and you can get at it by indexing into it. So here, Reg 1 is the model object. That was the regression object that we built. So we we did the regression, stuck it into Reg 1, and now I'm going to use a $sign and coefficients and just pick out the coefficients. So these were the coefficients, the same ones that we saw up here in the summary. Summary Reg 1. So these two coefficients. And what does that mean? Well, when you're writing, you're writing your own functions or you're doing your work, you want to do something with the coefficients. Maybe you want to plot them on their own, you want to put them in some kind of further calculation. You can get at all that stuff. Anything that's in the object, you can get to. So I have to move a little bit faster here, and what I'm going to do now, let me put that back up. You can follow along with the R code. I am going to move to running, looking at the HTML files. So I didn't want to do that. Let's see, where am I? Documents, RStudio projects, Data in Summit, here. And let's look at the RBasics HTML. Okay, so these are things that you need to know. This module answers the questions you're going to have tomorrow morning when you look at it. So I'm going to go through it quickly because, you're learning a new language, there are all these details, and your mind isn't necessarily ready on the to get the underlying details. But here they are. So your first look. So here's what we saw. We assigned, we saw assigning numbers to a vector, and that we execute v, which prints it out. The type of is another way to look at the actual storage type of the vector. It's a double, and the length of v is 1. Here's a way to build a vector on your own. C, concatenate, so C, open parens, some numbers will let you build a vector. You can see how long it is here. These are the contents. It's a double. It's 4. If you want to make sure you get an integer, a little quirk of R is to put an L after it. So that gives you integer values. So you can see you got integers, type integer. You can also force things or coerce things to be an integer. So another way of getting an integer would be to take u, which was double, and here this statement here is as integer u, it's coercing u to be an integer and assigning it back to u. So now type of u is an integer. So you'll see that kind of coercion, those things happening frequently. Here's a vector of characters. You can build character vectors, same paradigm. It's type character. Length is 3. So I've got 3 strings, A, B, C, D, E, F, and the third string is any old string. That's the text in there. Now what I can do is I'm making here, this is tricky, so that you can screw yourself up here easily I'm making the character vectors. I'm using the numerical symbols 1 and 2 and making them characters. And now it sees that it's a character. See? These are characters. I can coerce it into an integer too, if I want to. So logical vectors. R has the notion of a logical vector. Here I'm making a vector u4, and I'm assigning, so I'm drawing 10 numbers from a uniform distribution and picking out everything that is greater than 0.5. Then I'm producing, so U4 here is, this saying, is this greater than or equal to 0.5? And the first one was true, and the second wasn't. So this tells you you're doing a logical test on a vector. Vector operations, this is another way to build a sequence. What I did before was 1:10 to build the first 10 numbers. And you can see here I'm going 1 to 50 by 5. Again, repeating what we did 1 to 10. Here I'm adding the 2 vectors, and it's doing component-wise addition. So the first component with the first vector added to the first component of the second vector, component-wise multiplication. Here I'm indexing into a vector using a logical statement. So this is another indexing way to do an index, is the square brackets. So it's 1 dimension, and I have here this vector s, which I built here, which is the sum of these 2 things. And I want to pick out those positions for which v2 is greater than 5. Tricky thing. Don't worry about it now, but you can see it's going to be useful later. Here is a matrix. This is a way to build a matrix. So the matrix command, 100 numbers. I'm going to assign 10 rows and 10 columns. I'm going to have it built by row, and that means it's going this way. You can see 1 to 10. And then it's an object. It's type integer because there's all integers in there. It's a matrix class. So now you see there's a difference to distinguish between types and matrices. So we have here an integer class and a type, a matrix. It's got 100 numbers. It's 10 by 10. I can pick out the 5th element, so the 5th row of the 5th element, 1, 2, 3, 4, 5. The fifth row, 1, 2, 3, 4, 5. The fifth element, 5, 45. So it picks that out. When you do, you can raise matrix to a power. So here I'm raising, and again, this is component by component operation on the matrix. So I'm raising each component to the second power. I have a second matrix. I'm adding them together. And it's just, remember, it's vector kind of addition. So M1 plus M2, no loop involved. You just add the two matrices together. If you multiply again, you get two matrices, element by element multiplied. And then here, this is the symbol for matrix multiplication. So it's this paren, the star, and the M2, and now I'm doing your standard matrix multiplication. This function is it's going to pick out a subset of letters. It's going to pick out everything that's not equal to z. So I'm moving too fast for you to remember all this stuff. I want you to just have it for when you think, oh, how do you do that kind of stuff? I'm showing you some elementary operations. And notice here I'm building different kinds of vectors and matrices. R also lets you build arrays. Now, I don't even have much use for this, but you can see how advanced statistics and mathematical things, you might want to have multi-dimensional arrays. You can do that in R. More important is the list. The list is the catch-all data structure to put together various kinds of stuff. And here you see I have a list, the first component of which is just one number. The second component of the list is a vector. And then this component is a matrix. And this list actually, the fifth component actually consists of two matrices. And that's how this double bracket, whenever you see these double brackets, you know you're working with a list. And I got that from up here when I built the list. You can see the 1, 2, 3, 4, fifth, the fifth element of the list was itself a list. So list can contain lists. So this is the way you build complicated data structures. But you'll most likely be working with data frames, which I talked about before. And a data frame is a kind of list. And here is another way to build a data frame, So before we were working with data frames that were given to us. Here's a data frame that I'm just defining variables using that C structure. I typed all this out by hand. I put in some NAs. NA is the right way to indicate a missing value in R. So, you know, in various kinds of other platforms, people might leave them blank, or they might use some coded number like 9999. And when you look at a data set, of course, you have to figure out whether the values are real data, you know, real values, or whether they're some sort of code for missing values. In R, the convention is NA, and there are special kinds of functions for dealing with NAs. This is the function that builds the data frame. So first I have all these vectors, and then the function data frame, you can see, open paren, names the vectors, and binds them all into a data frame using the head function, dimension. Here's apply, and so I apply the class function to the data frame, and you can see now I've got something interesting. This sex is a factor. Sex is a factor. What does that mean? Factors are ways to deal with categorical data. So in lots of, you know, usually what you have to do is some sort of encoding. If you, you might want all males to be encoded as 0 and females as 1 or something like that. R takes care of that for you by actually having data structures to work with factors, because that's very important to doing statistical analysis. So it's a particular kind of type as a factor, something to keep in mind. And now, so you can see the class, it was a factor. you can do, here's a summary of the data frame. And when you have a summary of a factor, it just tells you what the levels are of the factor and how many there were of each. So it's smart enough, the summary function, smart enough to know what's going on. And now one more basic homework stuff. You're going to have to write your own functions every now and then. And here's how to write a function in R. So you see I got this keyword function, open paren x. That's showing you that there's, it's going to take one input. The squiggly brackets contain the body of the function. And what I'm doing here is just computing an average. So this is my Joe's mean, J-mean function. I'm computing my own average. I call the function by just putting in the variable name in there. So you see I computed the mean of Pmax. You can also, and notice that I explicitly said to return M. R returns the last thing it did inside a function that you make, but it's good practice to actually talk about what you're returning. So make that explicit. Here I'm doing another function, and I have a function within a function. There's something called a round function, which will round your numbers. So instead of just returning this output here, I'm rounding it to 2 decimal places. R has a nice feature where when you're working with functions within functions, there's 3 dots here. These magic 3 dots enable you to put in parameters for functions that are inside your main function. So make this explicit here. I'm going to tell, so I have this new function with the 3 dots. And now I can call it with Pmax, which is what this X stands for. And the 3 dots, because the 3 dots are here, I can give it a 3 because I know that the 3 is a parameter that the rounding function will take. And now it's rounded to 3. Function, yes?
Question about that. For the ellipsis, if first question would be, can you replace the ellipsis with another variable name and use the past, another example like that? And 2, what happens if you have 2 different functions that require
Right, so it'll be smart enough, it'll look up and it'll use the first one that it makes sense for. Right, and yes, you could put another variable in and pass it that way too, but it'd take a little more code. So that's kind of an advanced feature. I want you to see it because if you're looking at code, you're going to see that and say, hey, what is that all about? Look it up. Some things that are interesting for working with missing values. So here I'm building a vector. I have a missing value in there. You can't, the way to do a test, an equals test, is the 2 equal signs. But you see here it doesn't give me any information. So you cannot test whether something is a missing value by using the equal sign. The way I could test, z equals 2, I could test that. It's a concrete thing. But a missing value, what you have to do is use the function, is NA. So, so this is a existence kind of function, and it's going to pick out whether or not there's a missing value, and you can see it says that there is a missing value at the end, which is exactly what I did. Other kinds of things that are not are dangerous is nan is not a number. So if you divide by 0, you get a nan. So now I have something with a missing value and not a number. And this one little subtlety is that if I test is NA, it'll find both nans and missing values, which is good sometimes. But if you really need to know the difference, you use in nan, is nan. So now it says that this is a nan, this was not a nan, it was a missing value. So those kinds of distinctions. You can remove So here's the data frame. I'm going to, you see it has a NA in there. I'm going to remove all of the rows. In this case, it's just one row that has missing values in it. That's the easiest thing to do when you have missing values. It's also the most dangerous thing to do if you have a large data set. You know, you have hundreds of variables. You have, maybe you think you have hundreds of thousands or millions of rows, but if you do omit all the missing values, you might end up with no data at all. So that's very surprising. So the first thing to do is to check and see how many of them you have.
Question for you.
Yes?
Is it possible to replace NAs with a placeholder or something like that so that can be identified later?
That's not the way you really want to do things. You want to have NAs because you can always replace them with something else, but then you might treat it the wrong way.
Well, I mean, like, for instance, with a function like mutate or something like that, can you build another column off of something with flag and NA so you can separate it out later and identify it?
You could build another structure, yeah, to do that, you know, that tells you where the NAs are.
And Joe, for the recording, if you could repeat the question so the recording back here picks it up.
Well, the question was whether or not you can identify NAs in a different way. And yes, you can write functions that point into your array and pick out where the NAs are so that you can remember later where they are. That would be a sophisticated thing to do, but it can be done. So now let's move on here to something that's short but really important. You can execute this. So what I'm doing is getting data now from the web. So this URL is the location of a table that's out there in Yahoo Finance of stock values. And what I did was I went out to Yahoo Finance, and it tells you exactly how to do it. I looked up IBM stock, and then it says, you know, on Yahoo it says, okay, do you want this data? And it has a CSV file, and I just copied in the URL for what that CSV file is, so I know what that's going to be. But you see here that I'm reading it directly from the web, and you can do that right now. You know, read table, you'll get something that's read into a data frame. So pull something from the web kind of easily. You write it to disk. So here's a write.csv. So as I said before, it's going to be very common to work with interchange data frames and CSV files. You're going from one to the other. Here I write it to the disk. The syntax is, you know, IBM stock. That's the name of the data frame that I read in. I'm going to make a CSV file on my disk. It's going to be located in my working directory. You can tell where your working directory is if you type get WD. So get WD, open paren, close paren. That'll show you where your working directory is. That's where it'll write the file. And in this case, I'm saying that row names are going to be false. So I don't want any row names. Here's my working directory that when I built it's probably not the work. This is when I built the file back on my own PC. So you should see something different. And here I'm creating a directory. So I have a dir name. It's just a character string. I give it a path. This file path is an interesting function that binds strings together to make a complete file path. And here I got a warning because the directory already existed because it was the second time I did it, but no big deal. And then I wrote the file. You know, I wrote the data to a CSV file. Reading the file from the disk is just as simple. And then I want to emphasize here. So here's this remove is removing something from. So this will remove the IBM stock. So before I read it in again, what I'm removing is the data frame I already had, and I'm going to rewrite it again, bringing it in from the disk. So read table up here is the function that went and got the URL. So you fetch data from the web. Then you can read and write files to disk.csv files with read and write.csv. So basically, you're now at a point, I believe, where you can do useful stuff with R if you're interested. So if this kind of thing lights you up, then you can get data from the web. You can get client data that you have in Excel files or CSV files. You can already plot them, manipulate, get summaries of the data, manipulate them. You're already on your way to doing some very basic analysis. Now, and you're going to do it without writing any functions on your own in the beginning. What's going to happen is there's so much out there in the terms of analysis. Your first set of problems is going to be finding what you want. Now you know about LM. You'll see later on in the materials there's different functions for time series analysis. We'll look at some of that. But you're set. I mean, this is a point where the next pain point is going to be finding what you want, but there's a community out there to help you. So I'm going to show you here something that you won't be able to run here because of the way the network is set. Oh, yes. Yes. Is R able to read JSON? Yes, there are functions. There's the libraries and functions for reading JSON files. So you can scrape the web. You can find functions to, in fact, you just do scrape the web with R. You'll find your, Google that. You'll find the libraries. There's R functions to connect to almost every database known to man, all different kinds of data types. It's fully featured. We're not going to get to all that here today, but the way people, there's so much material out there now on R that if you're in trouble, you get an error message that you don't want, you put that in the Google browser and you'll get a Stack Overflow or some help with that. You put in, XML, reading XML with R, you'll get taken to the right place. So there's just a lot of material. So what I have here in this module is something for you probably to try on your own, but it's code that shows you how to set up and read a SQL database from R. So what it does is you have to first go off and get yourself an Azure account. So it uses the Azure ML account. And if you search on the web for, I think it's getting started, maybe Micheline, you could look for me. I wrote a blog post about 3 weeks ago on how to do this, to how all of the steps involved once you have an Azure account to set up a database using R, populate a table, and read it back. And that's essentially the functions that are in this module, same as in that blog post, but it has the screenshots. So let me just walk you through the concept here. You need some libraries. So now you see this is the way to load packages into R. It's a library command. The packages would already have to have been installed. That's a different command called installed packages. Or you can use the browser to install the IDE rather, the RStudio IDE, to install the packages. I'm loading in 3 libraries. One is RODBC. So this is the library that contains the ODBC connector to the database, from R to the database. There's another library package that has flight data, and I'm going to use that to populate a database. And now this dplyr is a function, a library that has some nice functions for manipulating data. We'll look at that in a little while. So once you've once you've set up your Azure database, you'll get a connection string, and this contains the credentials that you need to use for a database. So you can see you'll get a string, and that string will have the information, which I've left everything but my password. So you see here, that's the name of the server I was using, that's my username, and the password I was using, I was reading it from a file I had on my disk, and that's what you should do. You put your password, just a quoted string, you write it to a text file, and then read lines will read that password in. So that's one level of security. I'm giving it a database name. This is the driver. I got this information from that connection string. And here's the string. And this is the command operating on that connection string to establish the connection to the database that I had set up using, one click on Azure. On Azure. And then I looked at this. I read in this flights database just to get a table. So this is just some data. And this, which is grayed out here because I commented it out, this SQL save is what populates the database with the table data. So it's that simple. So I'm populating a SQL Server database in the Azure cloud with this just one line. The channel parameter is my connection, this thing that I build up here with all the credentials you get from Azure. The where is it? Yeah. So I'm taking this database flights and I'm calling it, I'm writing it to a table that'll be called flights table in the database. And then if you know SQL, you can query the database by using the SQL query command. So here is the SQL query command, the connection, and the SQL code. So it can be very simple. I'm not a SQL guy, but there are plenty of SQL people around that you can ask help from. But if you're a SQL person, there's this basic way to connect to SQL databases. So what I'm showing you here is R, the Azure Cloud, SQL, all wrote up in a little bit of code that's easily accessible from R. And that's part of the story about why R, so you can do these kinds of things. Now, if you're how many real SQL people do we have here? All right, so real SQL people. So the next step up is to get hold of Microsoft R Server, which is the proprietary extensions to R that Revolution Analytics developed and Microsoft bought and folded us in. And that has a family of functions that are big deal machine learning algorithms and generalized linear models and heavy-duty statistical models that will actually run in the database. So you don't move the data. So you can, you can write a SQL query and stick the R code right in that, in your, if you're a SQL administrator, you can write that SQL query, use the R code to do some analytics, and you can do the other way around. You can be an R person sitting at your desk and then pick out what we call a compute context that points to the SQL database, and then you could run your code in the database. So you can imagine an R developer, he's got like some table or smaller subset of data that he's just got on his laptop, or she has on her laptop, and you're testing your code on this small table locally to see whether or not it works the way you want to. Then when you're ready, you just point it to the database in the cloud or wherever, and it runs in the database there. So that's the promise of the synergy between Microsoft products and basic R. Yes.
Is that what in the 2016 version of?
Yes, that's what they're talking about. That's what they're talking about. So I'm running low on time here. Let me just show you. We've got till 10. I'm going to change things around a little bit. I want to let me show you what else we have. So you can see the next thing was this data manipulation, and this takes most time of all. I'll do a little bit of that to show you what's there, but first I want to jump ahead and show you what are in these other modules to give you a taste of things. So these are the ones for you to play with on your own. Let me show you visualizations here. So what I've done first off here is to take a data set in the car data set in the library, and I built the same plot with the 3 different plotting systems in R. So I want you to be able to recognize them. So you can look at the code later, but this is a kind of complicated histogram. So I have this data, and you can see it's got dollars here, and you have income from, this is the famous data set that talks about people with different kinds of education, and it characterizes them, whether they have a blue-collar job or a white-collar job or professionals, and the amount of education, looks at the income, and some sociologists measure a prestige that you get with that particular job. So here's a histogram of the money earned by blue-collar professionals and white-collar workers, and it's got kernel density estimates over it. So a kernel density estimate is a smooth version of a histogram. It's the one statisticians prefer to actually see whether your distribution might look at. This is the way it looks in base graphics. There's another completely different graphic system called trellis graphics that's about 10 years old now, and you see the same kind of data, but it's got different aesthetics to it, and it's got a completely different syntax from the base graphics. So it's there's a penalty for learning these different systems. The third system is the newer one that is all the rage. This is ggplot2, and it has a lot of support now because the grammar is actually based on a theory of how graphical structures should be constructed. And if I can just draw your attention to the code here, it's a little bit different than what you might have encountered in other places, and certainly different from the base R graphics. ggplot is the function. It's working on the Duncan data set here that we just had. You see the Duncan data set. And it's going to plot income, and that's an aesthetic. AES stands for aesthetic. And density means it's going to work with income. It's going to work with a density curve. And then what it does is I've assigned it to a variable. So P1, if I were to just print P1 at that point, you don't get a plot. What you have to do is build up layers of plots. So the next layer shows that the actual structure that's going to be used to render the thing is going to be a histogram. And then there's this facet which makes, these are the names for getting the three different histograms all in the same time. It's faceting them by type. It's one way that you're using a factor variable that I talked about before. Factors are the variable of that shows the different, whether you're blue collar or white collar. It's a factor. It's a categorical variable. So 3 different plotting systems. And down here, I show, you can see there's more examples for you to work through in the ggplot. So I tried to pick a bunch of examples with the code to be the kind of representative things that you'll want to do. And I'm just going to brush by them for you to look at on your own. Here is a time series of overflow data for the Nile, and you can see it's seasonal. The Nile overflows its banks every year at the same time. And just notice that I'm rendering this with lines, and the circles are actually the points of the data. This is the histogram that I had in my slides of box plots showing the distribution of flow by month. So you see the Nile is quiet, and then here's the season where it overflows its banks, and you can see there's great variability in the amount of overflow that happens every year. And this is an interactive plot that you can play with. And what I'm showing you here is a feature that goes to the heart of what I was saying before about whatever the next big thing is. Ours ambition is to somehow connect to it or make use of it. So right now, rendering plots on the web using JavaScript and web-based languages is the way to go. People are developing lots of things like that. You can do it from R. So you can build these kinds of plots because there are libraries that connect you to it. And you can see that there's not a lot of code here. It's using a library called digraphs. You load that in, and I'm building a time series object. It works on time series, and there's not a lot of code involved in doing this, and it's a pretty good interactive plot here. You can move things along, and also by having things on the web, you can share them easily. So something you can do. R3 plotting systems. There's also a module here for regressions. So what I've done is taken some data off the web that has to do again with cars, but a larger data set, and going through the summary functions, exploratory data analysis. So I've given you a paradigm of how you might do exploratory data analysis with R. There's a correlation plot. Now we're looking at a fancy plot to see pairs, how the pairs of variables relate to each other. Box plots of histograms, scatter plots. So this can tell you, here I have scatter plots colored by the origin. The origins are different, whether they were built in Europe or Japan. And it's kind of interesting. So now this is the kind of thing that you can do in R, or you might want to use a BI tool. Same thing. You can do this directly in R. R really shines when you fit the regression model. So here it's building a multiple regression model. And what I've done here for you is built models with different variables, numbers of variables. So this first model contains, so regressing miles per gallon against these 1, 2, 3, 4, 5 variables. The second model is 1, 2, 3, 4, 5, 6 variables. And the -1 means I've taken out the intercept. So that's the kind of thing you want to do if you're working with a categorical variable. You want to make and you want to take the intercept out, so all of the categories will show up. So this is the kind of thing, if you're a statistician or you want to learn some stats, that will be important to you. Just to show you that it's easy to do, and I've given you a paradigm. When you print, R knows what to do with the regression model itself. So the plot function, here I'm using base graphics, and this par command with the MF row set to 2 by 2 says that I can put 4 plots on the same device. So I could print this to the screen, or you could print it out to a PDF file. And these are the kind of diagnostics that statisticians get, are interesting to evaluate the goodness of fit of regression model. And it's, it's one command. Plot gives you all these kinds of things. A lot more work to figure out how to interpret it, but that's your homework if you're interested. The point is that R gets it to you easily. And what I've done here is assess the model performance by showing you how to put confidence intervals on each of the points. So it's plotting the fitted values against the actual values. It's putting confidence intervals around each of the fits. It's showing the regression line. So a good model has most of the confidence intervals covering, the regression line. You want to give the difference between a machine learning person and a statistician is the machine learning person gets a forecast and is happy with it. A statistician wants to know how good is the fit and is never happy with it. So depending on your psychology, you want to be happy, print the point and go with it. You want to know. Knowledge has never I don't know, in any field, knowledge doesn't bring happiness in life, does it? The more you know, the more you want to know, the more you worry about. So same with statistics. So anyway, enough of that. But there you go. And then the third one that I prepared for you is time series analysis. So there's stuff to fetch data in the beginning and create a time series object. So that's an interesting thing in R. You could plot just from a data frame. You could have a time variable in the bottom, and you have a whatever you're plotting, the overflow of the Nile, like we did before on the y-axis. But R is rich in kinds of objects, and when you want to work with time series, you probably want to work with a time series object because it automatically takes care of things like dates. If you're plotting stock data, you don't have stock data for every day, so you can tell the time series, where to start and where to begin, and it will know about leaving out the weekends, and so it takes care of all the details for the time series. And you can see that here. This XTS is a function in a library called XTS. I'm taking that closing stock data that is actually in the manipulation. It's fetched in the data manipulation module that I just skipped over. And it's ordering it by the date. Here's a raw time series plot. This is the baseline one you get if you just say plot that object. You can, here, what it's doing is limiting it from the beginning of 2012 to the end of 2013, so I'm screening out some data. Here's an automatic forecast. This is a beautiful thing. So if you work with time series, you might want to build autoregressive, moving average. Does anybody know what an ARIMA plot is? Okay, so there's time series people talk about regressing a time series on itself. So today's value as a function of yesterday's value. That's autoregression, or the past 2 days. Also, there's moving average kind of thing. You want to take the average value for 4 days in a row. That's a moving average. So sometimes you might want to fit your time series data to an autoregressive model, sometimes to a moving average model. This function, autoregressive integrated moving average, what it does is fit a model to a combination of that. There are lots of different parameters involved. This is sophisticated theory, but it's within your use now. You can build a model of a time series just automatically. So now we're down towards I'm encouraging the machine learning kind of mentality. Fit that model, and then you can forecast with it. So it gives a forecast, and it's done for you. You can see the forecast is, we haven't looked to see how good the fit is. We just fit the model, and the forecast shows you the spread, and the spread as you move out in time, it shows you there's more uncertainty. Well, what do you expect? And then I show you in this module that you can work through how to plot the forecast against the original data. And this is using ggplot. So now we have error bands. So here's the point forecast in the green. Here's the real data. And then these are the error bands. So it's not a bad fit for a first automatic kind of model. And I think this code will be accessible to you. It's not using a lot of different fancy stuff, but what it does is show you how to use the data frames to overlay all the data against the forecasted data. So that's there for stuff that you might want to go through, and I'll just show you now.
Joseph?
Yes.
Sorry, just a quick question. Once we have those visuals built, how hard is it to surface it in Power BI? Is there a sharing mechanism in Power BI that can retrieve things?
Well, what you would do is you could, and I don't know a lot about Power BI, but you could take the whole script and using the Power BI what they call connector, ingest the whole script, and then you can print out and that would develop the R plots directly, or you could use Power BI to render the plots.
And that's, just so we're clear on that, the Power BI has visualizations in it, so you could generate your data with R and visualize it with Power BI, so you certainly could do it that way. And as Joe's pointed out, there's actually an R integration in Power BI. You can also just print those out as Joe's been showing and just grab them off the screen and put them in Power BI, but it'll appear jarring. It's not a very pretty visualization, doesn't take advantage of all the features that you would have if you just use an R script in Power BI. And there are some blogs out there on how to do that.
Right.
Yeah.
I think there was a class yesterday that I didn't know if that was videotaped or not.
Yeah, the response here was that there was a class yesterday on doing that, and I'm not sure if that one's videotaped. I'm not either, but this entire conference, many of the sessions are being recorded, and as an attendee, you can get Joe's materials and other materials off of the conference website. You'll get an email how to download the materials, so you should be able to pull it from there. Thank you for that.
So this module here is about manipulating data. As you know, the bulk of work doing any kind of analysis is getting the right data, cleaning it, and then once you've got it even clean, then you might have to manipulate it into a format that you want. So what I've done here is point you to a number of packages that are written by this fellow called Hadley Wickham, who is a prolific package writer. And he's written an ecosystem. He wrote ggplot, and his mission in life is partly to make it easy to grab, manipulate, and visualize data. So these modules use the functions in the dplyr library to help you manipulate data frames in a simpler way than even having to index into things like I showed you before. So this is the modern way that people are developing things. And it fetches some data. In this case, it's IBM stock data right off the web, and also dividend data. So here you see I have, where would we put this? Here's the head. Notice that I use the same head function, but if you put a 2, I only get 2 lines. So you can control the amount of output you see. So you see the date, open, high, close, volume, the adjusted close. And now I'm reading in some dividend data. And what this thing does is eventually show you how to mash these things together. First thing you might want to do is mutate the data frame by augmenting it. So here creates a new variable. This is a dplyr function, mutate. It takes the data frame. It says the new variable will be called volatility, and it computes it. And it's also making the date a date object. So the date came in, it wasn't a real date object, it was a character string. So the function as date makes it a date, and that's the kind of thing that you need to work with time series. This prunes the data frame, it filters out stuff. So you can see here I'm going to assign to a new data frame data from the IBM data frame, but I'm going to take out everything for which the date is later than here. So it's dumping all the old stuff, and I'm looking at the tail, and you can see now it's only going back to 2000, which is what I wanted. This module, this bit of code here, shows you how to aggregate a data frame, which is a little bit tricky. First thing I want to do is make new structures for the aggregation. I want to pick out the month and year from the date. So this substring function goes to date, the date variable, picks out the 6th and 7th spot of the date structure. So 1, 2, 3, 4, 5, 6, 7. So that's picking out the month. And then the year is the first 4 characters, building new variables. You see they're here. I do an sapply again by class to make sure, I have a look at what what I'm dealing with here. I can see I got a date variable. The stock values are numerics or integers, volumes in integer. And then we got these month and year that I just made. This is the little tricky part of doing the aggregation. What you got to do is build a special data frame that has attributes for grouping things by. So I call it by. It uses the group by function. And what it does is take the IBM data frame, which just has year and month as variables, and it it builds in structures under the hood so that it'll help you produce a summary now that's grouped by year and month. And this is the syntax. Here's the summarize. So I'm using the group by function inside of the summarize function. See, I did group by first to get this data frame that knows how you want to group it. And if you look at it, you see how it makes, and I renamed the variables so you can see that these are the means of the opens, the means of the highs. And what happened here is now I have a data frame that is got monthly means. So it aggregated the data up from yearly data, daily data to monthly data. And then when you've done that, you can merge that with the dividends. It's a right merge, which means that I'm going to work with the way this is structured for this particular problem. I want to make sure I have all the dividend data and merge in the stock prices. So now I have 4 months and a year. I have the average of the stock prices and the closing values, and I have the dividends in there. Something that you'll probably want to do all the time. I find myself, whether maybe you're working with log data or time series data and you want to aggregate it up. This might be something that you might want to use another tool for, but this is the kind of point and click thing that's easy to do in Power BI, and then maybe you want to export that CSV file and work with it in R, whichever easiest for you. But what we're doing here is just giving you a flavor for how R goes about everything. And here is a common operation that you want to do. You want to reshape a data frame. Sometimes you have wide format, and you can see here, this was you have years, and then you have the months along the columns. And that's maybe, that's a common way you might build something in an Excel table. So you import an Excel table, and you go, oh, I want to build a plot with it. Well, you have to convert that to long format. And long format looks something like this. You have an observation for, 1962, the first month, January, 1962, the second month. So switching back between long format and wide format is something that happens frequently. And what I'm showing here is code to do that. So So this function is going to reshape the data frame that's in long format and put it in wide format. And then going back the other way, what we do is we take the data, use the gather, and we go back from wide format to long format. And the rest of the stuff that's in here is just showing you that it really did that, so you can measure them. So what I suggest now, in the time that we have left for a couple of minutes, pick something that interests you, and we'll be here to answer some questions. If you just work on the keys. Yes? So I think the question was limitations on the number of attributes that you... Observations, yes. So, okay, so the question is, what are the limitations on loading data sets into R, basically? Good question. R is memory bound. That means all of the data and all of your code has to reside in memory. Now, memory is cheap these days, but still you're working with larger data sets, liable to run out of memory. And that is why the Microsoft R server was written. So the data functions in that library are external memory algorithms. They don't work in memory. They work on a special columnar file structure, and they read in a little bit of data at a time. They do the processing and work on chunks of data and then assemble the final piece. And they're built to be inherently parallel and distributed so that you can run the same functions both on your PC but over a Hadoop cluster too, or some other high performance cluster. So yes, R has to be in memory. The rule of thumb is you want about 4 times the amount of memory as the largest data structure you're working with. So if you got a gig of a gigabyte of data you want to munch, then you better look at your task monitor and see that you have 4 gigs free for you to do your headroom for you to do your work in. Any more? Yes?
Give me tips or resources for people that are coming from other statistical packages like Stata or SAS, because this is very different than what I used to like.
Yes, so there's actually a book by Springer written by Bob Munchin from the University of Tennessee called R for Stata and SAS users. And it gives you an idea how to go back and forth between that. And you can find other stuff on the web if you search for it, but it's common. And that's the kind of thing that the Microsoft Consulting Group does too, help people with that all the time. Yes? Well, let's look, if you're still here before they throw us out, let's look at some code, pick up stuff, and we'll have Buck and Micheline if you...
So technically the session's over now, so you have a few minutes to get to your next sessions before they start, but if you do want to stick around before the next speaker gets in and sets up.
Yeah, we're happy.
Hi, whoa. Hi, I just want to address that question that was regarding R for like SAS users and Stata users. There's also, if you like videos, there's Data Camp.
Oh, he is?
Data Camp
So we got to go.
is like an R-centric site. So if you Google Data Camp, with a C.
Well, thank you all for coming. I hope I made some... Thank you.